Whoops, I wasn't quite ready. I'm ready now. Question 10, so a little bit on astronomy now. Always learn your astronomy stuff for paper one because it's triple only material, so you know it's high probability of coming up. The sun's got a mass of 2 times 10 to the 30. A white dwarf's got a mass, and it just says plug those into those. My top tip is on your calculator, use the fraction button. So it looks like it's got a, that's whole, that. Use that and use the up and down arrows to put these in, and make sure you use the times 10 to the x button. Don't start putting exponents in yourself. Stick to using that. So that's my only tip. It's just checking your calculator skills. So if you get this answer, your calculator skills are brilliant. If you don't, practice hammering some buttons on your calculator until you get the right answer. So put that into your calculator using that function, your fraction function, and then it'll spit out 0.17. Have a practice of that. If you get the same as that, happy days. Okay, next one. We've got something about main sequence stars and their luminosity, how bright something is. What's horrible about this is you'll see the scale is back to front. So they've done this to catch you out. They've given you a tiny clue in terms of that arrow there, but we can see it's going from higher temperatures to lower temperatures. So estimate the temperature of the sun, shove a line down. I get that about 6,500. So the mark scheme says anywhere between 5.5 and 7.5. So that's nice and easy, isn't it? Just find the sun, here, the sun. Read it down. Just make sure you're reading temperature rather than luminosity because it wants the temperature. State out the brightness of the main sequence changes. So what can we see? Well, it's getting brighter that way as we get an increase in temperature. And again, it's that stupid change of scale here to try and catch you out. So as the temperature increases, the brightness increases. It's more luminous, gives off more light. State how the brightness changes with mass. Low mass, high mass. As we increase the mass, we get more light given off. As the mass increases, the brightness increases. You can see as increases. Just state the different factors. Done. Next one, nuclear fusion provides energy source for the stars. Describe what happens during nuclear fusion. So we know we're going to take small nuclei, we're going to join them together. The problem is this nucleus is positive, this nucleus is positive, so they want to repel. So what do? We need lots of temperature and pressure. When this takes place, it joins to make a larger atom. Let's have a helium 2, 3. It's getting on its way there. It might also make a neutron. Okay. And then what we're going to say, so I could get in there actually, 2, and a neutron, but we'll go 2, 3. Let's leave the neutron out, but in some of these we'll make neutrons. So 2 small nuclei are joined at high temperature and pressure. This makes larger nuclei, but when this happens, a tiny bit of mass is lost, and this is converted to energy according to E equals mc squared. So a bit of Einstein in there. So small nuclei, such as hydrogen, are joined. There's your key word. This produces larger nuclei and possibly a neutron. You don't need to have that in terms of the mark scheme. High temperature and pressure are needed to overcome repulsion of the positive nuclei. I think that's a really useful sentence to get into your head, especially when we're later on in a higher tier question. This is because this is on the overlap. The highers have pretty much the same question. And then in the process, a small amount of mass is, in inverted commas, lost and is converted to energy according to E equals mc squared. And again, we could use this sentence again for fission when we're splitting them. A small amount is lost and this is converted to energy according to E equals mc squared. So nice question there. Next one, your favourite question because you're really, really good at it. A nebula may evolve into a main sequence star such as the sun. Explain how it happens. So we said, I've got a nebula, which is a star has exploded, boom, and left me a collection of dust and gas. But because it's randomly distributed in one area, I've got slightly more. This is now going to form the centre of a solar system. That is now going to form the star, in our case, the sun. Now, because it's got more gravity, because it's got more density, it's now going to pull particles in. And what we have to say is work is being done. All right? Because we're changing GPE to KE. We're making it move. So another way of thinking of this, and I've taught you fat, wobbly dinosaurs, I could equally write this as, in this case, the force is gravity. So this is work equals GD. And that work is now pulling in and it's compressing the gases. So work is done to compress the gases. That's really important to get in there. What now happens? Temperature goes up, pressure goes up, fusion takes place, and the star ignites. I said to you in class, I'd love to be there at the moment where our star was born. I'm sure that might even bring a tear to my miserable eye. Here we go then. So a nebula is a collection of dust and gas that's randomly distributed. In one area, there are more particles, it's got more density. There is an increased gravity in this area, and you could add in there that will form the centre of the solar system. This force of attraction pulls particles inwards towards this area. Work is done to compress the gas. That's the important thing. Work is done to compress the gas. And I've put in there force times distance or gravity times distance. Temperature and pressure increase until fusion takes place. We start joining the nuclei from this collection of dust and gas because it's so hot. Done.